Everyone, thank you for joining in. I am Ravishanjan. I'm a platform engineer at OLX, and today I'll talk about some of the learnings that we got when we provisioned and managed about 150 odd on-demand environments on a single Kubernetes cluster. It has been quite a journey for us, and along our journey, we have hit some of the bottlenecks, and I would present you the ways we have tried to solve those. So, without further ado, let's get started. So to set up a context at OLX Autos, we are running our own IDP, which we have developed from scratch, and we like to call it Orion. Just like all other IDPs out there in the market, Orion also have a feature of on-demand environments, with the help of which you can create an entire Autos environment, and each of those environment would house around 180 microservices. And as of now, Orion manages about 150 plus concurrent environment, 16K pods and 13K, around 13K plus Helm releases. And all of these environments are on a single EKS cluster. So what I have done is I have divided this talk into three sections, or I would like to say the lessons that we learned. In the first section, I would talk about how we identified and fixed single point of failures for all of our environments. As I've said that all of these environments are running on a single Kubernetes cluster. So there are some tools that are shared amongst all of those environments. So we'll see how it got in our way and how we solve those common issues. Next section will talk about how we expedited the overall environment provisioning time, since one of the use case of dynamic environment was to have it integrated into our CI system. So we wanted the overall pipeline execution time to be at minimal. So yeah, I will talk about that. And the last one is how we optimize the overall cost of an environment. So it is a no-brainer that we have used spot instances for this use case, but bringing in the spot instances have also bring in some challenges along the way. So I will talk about those challenges in that section as well. We'll explore about the first section first, which is eliminating your weak links. So as we scaled in terms of number of environments, we started noticing a weird issue wherein some of our workload was getting in crash loop back state for some reason. And this workload would typically include Prometheus operator, ingress controller, and API gateway. So you could imagine that these are critical to every single environment, and these were shared among all of the environments. So any outage and any of those can affect your performance and performance of all of your environment. So to understand this issue, let me refresh your memory about Kubernetes controller, how it works in general. So every Kubernetes controller use informers to apply a list watch on one or more Kubernetes resource, right? So this is the image which I have took from Nginx controllers documentation to how a controller works. So it would remain much same for all the controllers as well. So informer would initiate your list watch to one or more KTS resource, and along as soon as you uh, create, update, or delete any of those resources, you would register a handler along with that as well, which generally would enqueue all of those action along with those element into a worker queue. And at last, which is this controller, this is actually a reconciler in which you implement your business logic to how to handle those resources or how to converse to your desired state. uh, for the case of Nginx, it would be to configure your configuration. So most of the controller works this way in general. So one of the things which was the issue was, as we grew in terms of number of environments, our number of resources were also getting increased linearly. So our number of services, endpoints, pods. So for case of Nginx, it applies a watch on services, endpoints, pods, and ingress. And every time there is some change in any of those resources, a reconciler has to reconcile the configuration again and again. So this might not look much when you will consider a single environment, but let's say our environment right now comprise of, let's say, 100 services on an average, and we have about 80 odd KAT services, 40 app secrets, and these many Helm secrets and pods and endpoint. One critical thing that you have to keep in mind is we generally ignore Helm secrets, but for every release that you push via Helm, a secret is created in which we generally store your releases detail. And by default, the default history of Helm is about 10. And so these max at max it can create about 10 into 100, which is 1k secrets per environment. That is what I'm talking about. So you could imagine, if I'm talking about hundreds or 200s of these environments, how significantly will start increasing the number of resources and number of pods and endpoints. So this will definitely impact the performance of each of your controller. Two at a time, your controller would be in crash loop back state. But say, less for an example, if this would have to happen on your nginx controller, so all of your environments behind that nginx would be rendered useless. They would be just like burning money out there, because you won't be able to reach to those services because your controller has died. So one quick fix which comes to anyone's mind was will be to vertically upscale the controller, but there is a limit to how much you can upscale in terms of resources. So there should be a better way to handle this. And so the two learnings or two ways we can handle this is, first, always limit your controller watches. So any of the controller would generally include some of the parameters via which you can control the watches of that particular controller on the basis of, let's say, namespace or field selector. So definitely use those. From my personal experience, we have gained some significant performance improvement by limiting the watches itself. And again, there is a limit to how much you can limit those bots, right? Say for nginx, you have to watch services, right, of all those environment. But at that time, let's say we have limited everything, and that is also not even working out. So all of the another alternative was to limit the watches on per environment basis, or to segregate those controllers on per environment basis. So before launching the fleet of services of those environment, we can spin up a controller just for that particular environment. So this would be useful for the cases in which you have a very critical workload, which such as your API gateway or nginx controller. So in those scenarios, we have found out that generally spinning up a controller for that particular environment would limit the scope of single point of failure, because if we are having controller at per environment basis, then let's say for some reason our pod is impacted, the controller is impacted for some reason, it won't affect the other environments in the cluster. So yeah, these were some of the learnings. Moving on to the next issue, as we again grow in terms of environment, we started noticing that there was a very high response time on all of the services across all of the environments. So this was another issue that we got. And what we find out is that this was the issue related to DNS, just as always, right? It's always your DNS. So when we check, the current state was we were running core DNS. So a couple of pods of core DNS was working fine for us for a long time. But as we scaled, we thought that, okay, core DNS itself uses a Kubernetes plugin, which in further start a watch on the number of endpoints and services. So maybe again, it was the controller behaving weirdly. But apart from those also, we observed that there were a lot of unsuccessful queries at the core DNS logs. So one issue was that, and we noticed significant spikes in the resource consumption as well, because obviously we were scaling in terms of number of resources, so that was bound to happen. But why we were having some of those many unsuccessful queries, we'll discuss it in the coming slide. And core DNS was again a single point of failure for all the environment, because entire clusters services would be impacted if the core DNS was not working, as expected for some reason. This was another single point of failure in our scenario. So what we did is, so the issue of unsuccessful queries was because of a single dot, right? So to get into the details, you would see generally your all of your pods resolve config file includes three search domains. In For example, in this scenario, I have echo, which would be my namespace, and SPC cluster local, and this and this. So there are three search domain using every resolve conf of each of your pods, and this is your name server, and this is your end dot value. So what I've done is I spin up a pod inside the cluster, and I try to resolve this address platformcon.com. And if you would see, I have not appended a dotted last, which would mean that this is not a fully qualified domain. So you would see that number of queries that I have to do in order to resolve this address was 5. And herein you could see that the obviously the search domain was getting appended to each of our queries. So first time namespace.svc cluster, then svc cluster.local, and so on. So you would see that number of queries was 5, and number of unsuccessful queries was around 3. So obviously we were making some of the unnecessary queries there. So how to solve this, right? The solution was fairly simple. It was to append a dot at last, so it would make this a fully qualified domain name, and you don't have to search for all of those search domain that you have in your Etsy resolve. So in this scenario, you would see that we got only 2 queries, and we find any of the NX domain issues. So yeah, that was something. So we tried as a best practice to always include a dot at last, or use fully qualified domain name in all of our services. So with the help of this, we reduce the number of unsuccessful queries at DNS. So that improved our response time. But that was not it, because again, these queries have to be resolved by core DNS at some point, and you can imagine that there will be some point in future wherein this core DNS would run out of its own resources, and we'll have to manually intervene to upscale the core DNS pod again, and then the same story repeats, right? To how much you can upscale, or how to handle this, right? So just like the controller, we thought, using a same technique, that is it possible to distribute the load in terms of how we are scaling. So core DNS load should also be distributed accordingly, right? And one of the amazing way to do this was to use a local cache. So there exists a project called Node Local DNS Cache. You guys would have heard of it. So with this, what we do is we run this agent as a daemon set inside the cluster. So all of your DNS query, so it is again a core DNS application in itself. So it uses a cache plugin. So what it does is all of your queries are intercepted through IP tables to this particular agent, and if it is found in your cache, then it is returned from there. Else it will reach out to your upstream DNS, which is core DNS, the main kube DNS service, right? So implementing this helped us a lot, because as we grew, we increased the number of nodes, and on every node now there is a local cache of DNS, and those would be used before reaching out to your core DNS. So we distributed the load at the main core DNS to these local DNS caches, right? Now again, right, so there is again a single core DNS which again has to resolve some of the IP addresses at some point. So we have to ensure that those core DNS main core DNS instances also horizontally scales as we expand our cluster, or by expanding I mean number of environments. As number of environments are getting provisioned, it should horizontally scale itself as well. So there is another tool that you can use, which is cluster proportional autoscaler. Now using this, you could set up a linear or a ladder based scaling policy in which you can specify your cores or your number of nodes. So you could make a linear growth. Let's say for every node you want a single core DNS instance, or every 4 node you want a core DNS instance. So as you grow in terms of number of nodes, you can upscale your main core DNS instance as well. So you could have a linear policy or a ladder based policy to horizontally scale your core DNS instance as well. So yeah, combining all these three, the fully use of FQDN and implementing node local cache and proportional autoscaling, we were able to significantly reduce our response time. So herein you could see a graphical representation of our uh, benefit that we got while implementing those three strategies. So yeah, that now comes to another section. So it is about how to expedite the overall provisioning time so as to improve the overall pipeline execution time. So let's see. Okay. So what we did is we introduced some of our static provisioner, and so we do understand that we will be wasting some compute, but we were able to compromise some compute if we can gain some of the improvement in terms of provisioning time. So what we did is we spawned some of the POS containers, and those having the pod priority uh, less than the actual workload. So it ensured that we have some certain instances always lying around, which could be utilized by an environment. So let's say if our CI is triggered, we can use those instances or those nodes to provision the actual workload of the environment. And so they don't have to wait for a node to actually be provisioned or registered with your Cube API server. So we save those precious around 5 minutes of the time by making use of those over provisioners. So another thing that we did was to maintain an warm IP pool. So we are using AWS VPC CNI in this scenario. So by having a certain pool always there, we can ensure that every time a new pod comes on to your node, it no longer has to reach out to your service provider. For example, in our scenario, it has don't have to call your EC2 API every time it needs to get an IP, right? So you can tweak these settings using your minimum IP target and warm IP target. But I would suggest to carefully make the decision of what your target pool should be. Don't get don't go too overboard on this, because if you have limited IPs in your subnet, then this might trigger another issue of your IP exhaustion. So what we did is we found out a solution that most of our instances are sharing same type of compute. So let's say 8x large, so we'll be using M series 8x large, C series 9x large. In that scenario, we have, in terms of CPU and in terms of memory, we have consistency in terms of nodes, right? So we calculated our average pod density at that time. So we set this minimum IP target to be that value. So every time a node is provisioned, there is always, let's say, if our pod density is 20, then we'll have a 20 IP address always in buffer, right? And warm IP target, we kept at one because we wanted to conserve the IP there. So using this, what we did was every time the pod was getting provisioned on any of the node, it always has to, it could easily fetch the IP from a local IP address manager, and it does not have to call your main EC2 API to fetch that address, right? Not recently, but uh, AWS CNI now also supports prefix delegation, and now what they are offering is you can, every time a CNI is provisioned, that CNI will bring in a /28 subnet address along with it, so which calculates to about 16 hosts. So by enabling this and maintaining a warm prefix, again, let's say of one, you would be maintaining a buffer of around 16 IPs. So till 16th pod, you don't have to invoke any of your EC2 APIs. On the 17th pod, you'll have to invoke a call which would extend your uh, prefix to more 16 addresses. So either of the way, you could use any of them. We tweaked it using minimum IP target. So with the help of this warm pool in conjunction with over provisioner, we ensured that every time a new environment is to be provisioned, there are some certain IPs reserved for it and some compute reserved for it. And we noticed a significant improvement in overall uh, time reduction that we were having earlier, right? So yeah, now let's move on to our last section where we will discuss about how we leverage spot instances uh, for the case of on-demand environment. Dynamic environments were ephemeral in nature. You could create them or destroy them at any point of time. Though some were long-standing environment as well, we saw that it fits a perfect case to use spot instances, right? So it was a no-brainer for us, and we did implemented all of our fleet using spot instances. But using spot instances bring in a couple of challenges with it. So these two are the one which bothered us the most: the spot interruption and limited availability. With spot interruption, as you guys know, that the spot would be taken back at any point of time with a notice before in around 2 minutes before. And the other one is its limited availability. So we were running a single replica of all of our applications, so we need to ensure that we gracefully handle those interruption, and every time our environment is getting provision, we needed to ensure that compute is there to support that environment, right? So to solve these two challenges, what we did was, this is for spot interruption. So there is a project called AWS NTHR node termination handler. This is something which I have prepared. So what it does is, uh, let's say if your fleet is you are running on EKS cluster, and you have an auto scaling group or the EC2 instances, what you can do is you can create some events in your SQSQ using an event bridge. And if there is any event of type EC2 spot instance termination warning, you could enqueue it to that particular queue. So every time any of the spot is taken back from AWS, an event is to be placed inside your queue, and there is another agent running inside your cluster, which is this NTH pod here. What it would do is it would dequeue that particular event and the details to which instance is going down, and it'll gracefully move out your workload. So it'll first cordon that workload so as to avoid future pods getting scheduled on it, and all of the existing pod would be drained properly to another node. So this was an amazing way to handle the spot interruptions. And there is couple of ways. So this which I explained you was using a queue processor, but there is another way which is using instance metadata service monitor. And if you'll go by this path, then you'll have to deploy this nth using daemon set. So what it does is it listens on your instance metadata service address for EC2 events, and whenever there is a termination uh, going, it'll do the same thing. It will cordon and drain out that particular node. So this helped us in handling those spot interruption. And the another piece was to how to handle the unavailability of spots. So let's say if you are using 2x large instances, and if M5x large is not available in your region or in your AZ, then how to handle it. So first and foremost, this most of us know that instead of using a single um, instance type, what we could do is we could create a launch template and include bunch of similar compute instances together. So here, and let's say all of the 2x large of different series I have included for, let's say, M5, M5A, M5D. So we could include a bunch of these instances inside a single launch template. So let's say if M5 2x large isn't available, so we could switch over to M5A 2x large, right? So let's say even if all of so this helped us reduce or tackle this unavailability issue to some extent, but we noticed that in some scenarios all of those instances were also not available, although it was uh, less frequent, but it was an issue. So what we did is we used cluster autoscalers priority expander. So what you can do to handle those scenario is in cluster autoscaler there is a expander configuration which you can pass in. So in for example, what I did is I use this configuration of expander. So in this I assigned some of the priorities to our node group. So here in this on demand is basically the node group in which the launch template would contain on demand instances, and the spot is a node group which contains all of these spot instances. So now what will happen is since the priority of spot instances is higher, so first it will try to launch all of the spot instances using this launch template. So it will try to first do the launch of your primary instance. Let's say M5 2x large in this case, but if 2x large isn't available, it will check these kind of instances, and if all of them are not available, then it will fall back to on demand instances in our scenario. So it would ensure that at no point in time your cluster is exhausted out of your compute. So this would ensure that every time, let's say, a CI is triggered, there is compute available to you so as to provision your environment. So yeah, I think this sums it all. So using the spot instances and managing the potential shortcomings of it, we were able to confidently run all of the all on-demand environments on Spot Fleet. As of now, we are managing all of the environments 100% on Spot instances. And with that, I would like to sign off. I hope you will find this talk useful. If you have any doubts, I'll be available today on the Slack.